Hello, this video is entitled Differentials. Now, the first thing before we get to differentials, we're going to talk about what's called a tangent line approximation. Now, in my class, I no longer cover Newton's method, so don't worry about that, but that's okay. Now, let's see. So look, we've seen the idea, obviously, of the tangent line, at a point on a graph. But notice in this particular graph, we're going to, let's call this a tangent line or a linear approximation. If you wanted to approximate values of the function near that point, your tangent line could be a pretty good approximation. Now, I'll tell you the truth, this is, pretty much an old school sort of idea in a way with, modern calculators and technology and stuff. But anyway, I think it's interesting to take a look at. But you see, if you pick values on this graph close to the tangent line, you're okay. But you can see as the graph moves away from this point C, the y values, the red and the blue there, start separating. So you would not, for example, the tangent line to approximate the y value of this graph, say over here where I have the dot, so that would be a pretty bad approximation. But near the point, the tangent point, it would be okay. Now, in Cal 2, we actually look at polynomial approximations, which are actually even better. In other words, fitting a curve near a point. I'm just going to draw a little rough sketch here. So, let's say that was the same point. Hopefully, I'm using a mouse. So since I'm using a mouse, I can get close here. But let's say it goes in there, curves in, and goes something along like that. Which that would be a polynomial. That would be a lot better approximation than just the tangent line. Let's get rid of all that. All right. So we're using basically the point slope form of a line, which I then essentially they rewrote sort of y equals mx plus b. Well, not actually. We're going to finish it. It's not technically y equals mx plus b. It's the point slope with y1 moved over to the other side. So y1 is f of c, and then f prime of c, m, the tangent slope, that's that right there, and you have x minus c. So, but we will finish the problem with in y equals mx plus b form. So here we're going to say, now we need the value to be pretty close to the x, which it is in this problem. So if f of x equals the square root of x, at the point 4, 2, find the tangent line approximation and use it to approximate the square root of 3.9. And that's what I was saying about this sort of being old school here, because modern day calculators and things, and even, calculators from 30 years ago or more, put in 3.9, get the square root. Anyway, with that being said, here's the derivative of f of x, 1/2 x to the negative 1/2. You plug 4 in there, you're going to get 1/4, because 4 to the negative 1/2 will be 1/2. So you have 1/2 times 1/2 makes 1/4. So I know my slope is 1/4. My f of c right there is your y value 2, which of course we could have easily calculated that 2 ourselves by putting 4 in there. So you have 2 plus 1/4 x minus 4. And then I just solved it to put it in y equals mx plus b form. That's just the way I prefer to do it. So distributed, combined terms. So the tangent line approximation equation would be y equals 1/4 x plus 1. And that's essentially the same as the graph, the equation of the tangent line that we got before. They're just doing it a little bit differently, but you could still come up with this doing it the other way we did it. Where I would have said y equals 1/4 x plus b, I would have put 4 in for x, 2 for y, and I would have solved for b and got 1. So that's still valid. You can do it that way too. Well, anyway, let's see how it turned out for 3.9. So I put in 3.9 into this equation, which I did right there in the calculator, and got 1.975. And then I used whatever, I'm not sure what algorithm the calculator uses to compute square roots, but obviously it's much more precise than what we're doing. So they're saying the square root of 3.9 is 1.9748. So our approximation was not too bad at 1.975. Pretty close. As long as you stay close to your x. And I just graphed it for grins. So you see that tangent line's holding it pretty well. Actually, there's 4 right here. Get a little, it's hugging it pretty good. Obviously other curves, it might venture off quickly, like if you had something like this, maybe, and then the tangent line was doing this. So, then it separates a lot quicker. That one's actually riding alongside it pretty good for a while. And then I just put in the calculator, just showing you some of the values. Obviously, 4, they're going to be the same. Whatever your x is, the tangent line and the graph are touching each other. What you see as you start, drifting away from this, like that was using 30, but even 12, 3.4, 6 versus 4. So it's only good if you stay in the immediate neighborhood of the x, or like really close by. Now here's sine of x at 0, 0, and we want to approximate sine of 0.1 radians. Okay, so derivative of sine is cosine. F prime of 0, put in there for x, we'll get 1. F of 0 would be 0. And actually this one just turns out being y equals x. All those zeros there, yeah. The line y equals x is the tangent line approximation. So when you put 0.1 in there, you're going to get 0.1 for y. So the tangent line approximation for sine of 0.1 would be 0.1. Now let's see what the calculator has here. Calculator has 0.1. Okay, they have 0.99983. Well, that's pretty darn close to 0.1, so I think our approximation is pretty good, as long as we stay near 0. And I mentioned it right there, so let's see what we have. Now it's time to move on to the highlight of the chapter here, differentials. I mean, the section highlighted, not the entire chapter, just this section. Differentials, after you see it here, you never see it again unless you take Cal 3. Then it comes back. Oh, wrong way. Okay. Now I copy this graph textbook. It's okay if you don't totally see what's going on here. Well, anyway, what we are actually doing is we're going to use the derivative to approximate what an actual change in a y value would be from when you go from the first x to the second x. So what this picture is saying, okay, the delta x notation is okay here. I got rid of it earlier when we were first learning derivatives. I changed it to h because it made some of those problems more confusing, but I think it's okay here because we're not going to be multiplying and combining terms together. So this is just on the x-axis here. It's just a fancy way of saying, x1 and x2. It's just that x2 is x right here plus whatever this delta x here, which is also known as dx. dx and delta x are exactly the same. But dy and delta y are not the same. They're close. That's the idea. We are using dy to approximate delta y. So is it whatever color that is, some sort of bluish green looking color there. But anyway, as you go from these 2 points, you see here's the y value at the first point right there that they labeled s, and this q is the y value at the second point, and then that would actually be the difference in the function value. Is that delta y right there? Y went from p to q. Now keep in mind this delta y could be a decreasing value. Obviously a downhill graph, when a decreasing function would have a negative delta y, which that's all right. So delta y doesn't have to be positive. And then the tangent line approximation right here then it's showing they're using dy, meaning how much is it changing on the tangent line. So dy would be that amount right there, which isn't the best approximation, dy for delta y. It usually works pretty well. The delta x needs to be pretty small for this to work out. It would have been a lot better like somewhere in there versus over here. But anyway, if you, as long as you can kind of calculate it, if you don't get overly bogged down with grasping all of it conceptually. It's not that difficult to calculate, but students often get confused between the dy and the delta y. Now the dy is basically going to be calculated as f prime of x times dx. Now if you notice, that's just regular derivative notation. It would be like if you had dy divided by dx equals f prime of x and you move the dx over. That's kind of the same idea. So what we're going to do is find the derivative, plug in your x. The x will always be the starting value, first point, whether it decreases or increases. And then dx will be the change, and that's going to be our dy. And then literally the delta y is just basically f of x2, this part right here, f of the second number minus f of the first number. Like if your x was moving from 2 to 4, delta y would be f of 4 minus f of 2. So we're saying it should be fairly close to this dy value right here. All right, so here's it written out here. The differential of x is denoted as dx. Dx and delta x are the same thing, but like I said, dy and delta y are not the same thing. So the dy is calculated as f prime of x dx, which also can be replaced with delta x. So I think the best thing to do at this point is just kind of jump right in and try this out. Now this one's not using points on the graph, it's just finding the general differential, meaning just writing the differential in that notation. And this notation is going to be important when we start chapter on anti-differentiation and integration. We're going to be using this differential notation. So to find the differential of this particular function, that means, yes, you're finding the derivative, but you're just writing the answer. Instead of saying like dy dx equals all this stuff here, you're just leaving the dy here, and you're putting the dx next to the answer. That's all it is. So that would be the derivative. You have x to the 1/2, x to the negative 1/2, so it'd be 1/2 x to the negative 1/2 minus 1/2 x to the negative 3/2. Okay, now let's get to the kind of questions here that you're likely to see on one of my exams. Could be also on the quiz or something, but this is kind of what you need to be able to do here, is just calculate these two values. So here we have, for this problem, we have y equals 2 minus x to the 4th. We're saying that x equals 2. So instead of giving us what our second x value is, they're just telling us that the delta x dx is 0.01. Now that could be negative. I think I do an example coming up with it negative. So that just, what that tells you is that means x is going from 2 to 2.01 because that's a positive result. So you see, it's always, the second value is always 2 plus delta x. But like I said, if delta x is negative, it'd be 2 minus that, 2 plus a negative. So it's okay for this second number to be smaller than the first number. That's all right. So here, basically, all I'm trying to find for the delta y is literally f of 2.01 minus f of 2. And based on the function y equals 2 minus x to the 4th, you see I sort of typed it in manually up here. I got negative 0.3224 for that result. Now let's use the differential, which is designed to approximate this number, to get close to it. And let's see how close it gets. So I need to take the derivative of this function, which is super easy, negative 4x cubed. So to find dy, I need to find f prime at 2, always your starting x, times your dx value, which is 0.01. So to find the dy, all I have to do is take f prime of 2, multiply it by 0.01, your dx. So f prime of 2 right here would be negative 4 times 2 cubed times 0.01, and I get negative 0.32. And that's pretty close. So there's not exactly rule of thumb for how close you have to be on this exactly, but you know, if you got negative 0.3224 here and you get like negative 6 point something, you know you were way off. So there's no exact definition of how close it should be. Here's another one. Y equals 1 minus 2x squared. We're saying x is 0. We're saying that dx is negative 0.1. So we're actually, the x is decreasing. It's because the graph's going to the left, which is fine. The derivative is negative 4x. So literally here, since it's negative 0.1, 0 plus negative 0.1 would be negative 0.1. So the delta y would be f of negative 0.1 minus f of 0, which I did right here and got negative 0.02. And then dy would be f prime of 0 times delta x. So it's negative 4 times 0. Well, it's game over right there, but let me, negative 0.1, that is 0. I just used 2 decimal places. Well, that's okay. 0.00 is pretty close to negative 0.02. So that's probably a good result. Now this next one's kind of an interesting example. I'm not going to really ever put this on a test or anything, so I might stop here for a second or maybe go through it real quick, or leave it enough if you wanted to pause the video and just look at it for yourself and see how it worked out. But it's using the differentials, and like I said, this is kind of an old school method. You know, it's how I might have done this back when I was a kid, just as calculators were coming on board. So yeah, you're using it to approximate cube root of 66, and we're using 64 because that's the closest number to 66 that has a cube root we can evaluate easy. Cube root of 64 is 4. So if 64 is close to 66, so this should be a good approximation. But like I said, don't worry about this. I won't put this on a test. But I want to jump down here to the answer. Now, I was able to work this out because of using that 64. And you know, this could have been done without a calculator, at least theoretically. I can, but anyway, you can get an exact answer of 97 over 24. That's what it would be. And then, of course, I converted that to decimal. Now, I did the cube root of 66 in the calculator and got this number, so whatever algorithm they're using. But heck, our approximation is actually pretty good here. 97 over 24 for the cube root of 66 is pretty good. Look at that number compared to the one above it. That's a darn good approximation. But no, I don't put these radical approximation problems on an exam. So. Now here's another example. Oh, actually, this is the first sort of application type of problem that we might use for these differentials. They're commonly used to if you're trying to estimate measurement errors based on the possibility of your measuring device being off a little bit. You know, perhaps if you're allowing that it might be off some small amount, how does it affect the overall measurement? I wouldn't worry too much about the terminology per se, but this exact value, that's fine, but minus measured values, kind of problem is the exact value is we're not often sure. And then that delta x is called the measurement error, and this delta y is called the propagated error. The problem is we don't 100% sure know if the exact value is really exact, so we're going to use the dy idea to approximate what that error would be, because calculating that error is somewhat impossible. All right, this caliper micrometer, suppose we're allowing for the possibility that it's off by, and it's telling us in the problem here, we didn't just make that up, say maybe plus and minus 0.01 of an inch. So let's say that we're going to, in this example, we're going to find the propagated error, 4 decimal places for the volume of the ball bearing with a measured radius of 0.7 inches. So we're measuring this to be 0.7, but now we're trying to measure then, okay, if that's the case, how far off could we be overall on the volume? What's our range that we could be off on the volume of that, whatever you want to call it, ball bearing there, yeah, what they call it. Okay, geometric formulas like these, you would be given the formula on a test. I always give those. However, this work here you have to do. Now you have to be careful on this problem. This is really, it's easy to confuse this with related rates, but it's not related rates. We are actually taking the derivative of v with respect to r, not like dv, dt, dr, dt like you have with related rates. So that's why I can see that being a little confusing. But if you can actually skip this middle step and just go from here to here, and just say that dv then would be, take this derivative of r cubed, 3 gets rid of 3, you have 4 pi r squared dr. So that's just in differential form. It's the derivative of v with respect to r. But just from my experience, that's what I've seen students be confused with, is thinking that was related rate. But you'll know when it's a related rate problem versus a differential problem. The question itself is not designed to trick you by any means. So yeah, you'll see related rate would be asking about rates of change and things like that. This will not be asking a rate of change. So your dr plus and minus 0.01, r is 0.7, those are given to us. So the dv would be 4 pi times 0.07 squared times plus and minus 0.01, which gives you plus and minus 0.0616 cubic inches. So that's the allowance that we're saying, okay, we got 0.7 as a measurement, which we could then report what that volume would be, but then we're now saying this represents the possible error in that result. Okie doke. How about the next one? All right, we're measuring the edge of a cube, 15 inches. Now we're saying perhaps our measuring device could be off by plus or minus 0.03 inches. So we're allowing for that to be a little bit off. So then let's use that information to calculate how far off the volume of the cube would be and the surface area of the cube would be. Now, unlike that volume of that sphere, you should be able to calculate these results just, kind of common sense. They're not specialized like a sphere or a cone. I mean, a volume of a cube is just going to be x times x times x. The height's definitely x because it's a cube. Surface area. Now, I guess the only issue, you assume it's a closed box unless it's telling you otherwise. So you would assume that the top is closed also. But anyway, each side would have an area of x squared. So that cube has 6 sides, 4 around the side, top and bottom. So the surface area would be 6 cubed. So now I'm just using x now instead of r. But so the dx would be plus and minus 0.03. So the volume would be x cubed. So dv would just be 3x squared dx. So we put in the 15 for x. We put in the plus and minus of 0.03, and we would get plus and minus 20.25 cubic inches. So we would expect the volume that we reported, obviously the volume you're going to report is going to be 15 cubed, because that's what you measured. So then we're saying, okay, that could be off by 20.25 inches either way. The surface area, so ds would be 12x derivative of 6x squared, 12x dx. So I put in the same 15, I put in the same plus and minus 0.03. I get plus and minus 5.4 inches squared. Now let's talk about something called relative error and percent error. Now you look at those numbers and you like this is using the numbers for the last problem, by the way. So we're saying plus for the volume, the plus and minus 20.25 inches. That sounds like a lot, sounds like a big number, but really it's all relative to what the actual total volume is. So this relative error would be calculating the result that we got, dV, and just dividing it by the actual volume itself based on that number. So we took plus and minus 20.25 and divided it by 15 cubed. It gives you a number of plus and minus 0.006. Now that number doesn't have any units because essentially the inches cubed would divide out. But a better way to kind of really get a feel for what this number is if you convert that relative error to what's called a percent error by multiplying it by 100 to make it a percentage. So if you take that same number right here and multiply it by 100, you get 0.6 plus or minus 0.6%. So now the way you can look at it is that 20.25 cubic inches means we're off of our measurement of the volume by less than 1%. So whether that's acceptable or not, that's a personal issue, But so the 20.25, sounds bad, but within 1% maybe doesn't sound so bad. Plus or minus 0.6% of the overall total measurement. So that's what this is saying. So here is the same thing for the surface area. We take the ds, which we got up back above the page, here's 0.5, there it is, plus or minus 5.4. Divide that, the surface area would be 6 times 15 squared, because it's 6x squared. You get plus or minus 0.004 for the relative error, and then the percent error would be plus or minus 0.4%. So that measurement is also less than 1% off. Right. Now we're going to do one with 2 variables. Just to add a little bit of interest to this. Throw a little product rule in there. So let's say we're measuring a triangle. And of course, the area, unlike the surface area and the volume of that cube, triangles with one measurement. This is triangles dependent on two things, the base and the height, 2 variables. So there's the area of the triangle, 1/2 base times height. So it said that you measure the base at 36, you measure the height at 50, and the possible error measurement of each side is 0.25. Use differentials to approximate the possible propagated error in computing the area of the triangle. Also find the percent error. I just kind of skipped over the relative error anyway, but obviously you're kind of getting the relative error when you're getting the percent error. So just in a product rule, so you see the measurement error though, it's the same, using the same device to measure both of these, so that's why this is the same number. So I did the derivative of f prime of b, which would just be db times h, plus f, which would just be b times the derivative of h, which is dh, and then the 1/2 right there in front. So that's the trickiest part I think about this problem is just that derivative with the product rule. After that, it's quite easy. So you put in the 50 for the h, the 36 for the for the b. Looks like I reversed the numbers there, but they're both right. So that dh is right there, 36 for b, and then the db and the dh are the same number. Plug it in there, you get plus or minus 10.75 centimeters squared. So you see I take that dA divided by the area of the triangle, which is 1/2 times 36 times 50, and there's your 10.75, straight out multiplied by 100%. So this one's off by a little more than 1%, 1.19%. All right. Now we have this problem, which is measurement of a circumference of a circle is found to be 64 centimeters with possible error of 0.02 when measuring the radius. Approximate the percent error when computing the area of the circle. Okay, this one's a little bit tricky because it's not giving you what the radius is. It's giving you the dr dt. Forget what I just said. The dr, not dr dt. I started thinking about related rates for a minute. The dr is a plus and minus 0.02, but it's not giving you the r. But since it's giving you the circumference of the circle, it's allowing you to solve for the r. So 64 equals 2 pi r. R equals 64 divided by 2 pi. So that equals 32 divided by pi. So I'll just leave it like that when I put it in the next formula. I won't convert it to a decimal. So then if area equals pi r squared, dA would be 2 pi r dr. And now we have what r is. So it's 2 pi. See, now that's why I left it this way. The pi's conveniently cancel out. So it's 2 pi times r, which is 32 over pi, plus and minus 0.02. And then that would work out to be plus and minus 1.28 centimeters squared. So you take the percent error would be that number divided by pi r squared. So it's pi times 32 over pi squared times 100%. And you can see I did it right there in the calculator box. And this one you'll get plus 0.39% error, possible error, for the measurement of the area of the circle. And we've got one more. Actually, two more here. That's okay. Just added a couple here. That's fine. So let's see another circle problem, but this is not worded like the last one. Area is pi r squared. How much does the area of a circle decrease when the radius goes from 5 to 0.48? And so this one, they're actually, now this is a little tricky because it's not a measurement error problem. This is just going back to finding what how much the area would change by. It's more just a straight differential question. It's not propagated error. So if we're going from 5 centimeters to 4.8 centimeters, that means our dr value would be negative 0.2 because it's decreasing. And the r is always the starting value. It's always the first value. So it's 5. And then because it goes down by negative down by 0.2, that makes that negative 0.2. So all you have to do is take the derivative dA equals 2 pi r dr, put in 5, put in negative 0.2, and it ends up being negative 2 pi, so it's approximately 6.3 squared centimeters. Now you might think, why do I have negative and they have positive? It's because they use the word decrease. So in other words, you're saying decrease by a positive number is saying increase by a negative number. See, my problems are always set up in terms of increase. So if increase and you get a negative, by definition, that is decrease. So that's, yeah, I would not trick you with anything weird like that in an exam. I mean, you would not have like a positive and a negative result there. Either I would say increase and make them all negative, or word it like this and leave them all positive. So the last one here is a delta y and a dy. I guess I just felt like adding another one in there. That's good. So x is 2, delta x 0.3. So we're going from 2 to 2.3 because it's x plus delta x, as I have right here. So the delta y would be f of 2.3 minus f of 2. It looks like I didn't show any work here, but I'll just tell you what I did. Put in 2.3 right here, everywhere you see an x, and get a number. And then put in 2 right there when you see an x, and subtract those two. This might be a good one for you to practice here. So, or I guess I could do it real quick. Yeah, I guess I could bring that up real quick in the calculator and put in. It was 2x squared minus 3x plus 5. So I'll quit out of this, and I'll use the function thing. Vars, y vars, function. This is like saying f of 2.3 minus f of 2. All right, so now I'll copy that back in there just so we can see it. And also, it was 1.68. That's good news. And then the differential would be the derivative. Before x minus, I went ahead and just kind of put the dy right there without, I didn't formally write the derivative. I suspect I probably just added this example one semester real quickly, at the end of the notes. Maybe a student requested, hey, can we see one more of those? So I probably did it right near the end of a lecture period. So there's 4x minus 3. That's your f prime of x. And there's your dx. So before, and x is 2. So, got a problem right there. Hopefully the answer will still be right. Maybe it's just that should say, that should be 2 there. So it's 4 times, yeah, the answer is right. So this is a 2 right here. 4 times 2 minus 3 would be 5. 5 times 0.3 is 1.50. So yes, I must have been in a hurry when I was doing this. So I'll change this to, that should be a 2 right there, but the answer is correct. So it's a little bit off, but 1.5 for approximating 1.68 is a little bit off. And so that concludes this lecture on differentials.